Welcome to the 6th module on real-time simulation of fax devices using OPAl RT. In today's session, we are going to see the basic working principle, control scheme as well as real-time simulation of TCSC using OPAl RT. Now earlier while discussing control scheme of STATCOM, a shunt device, we have seen that the shunt compensation is effective in maintaining the overall voltage profile of a transmission line. However, it is ineffective in controlling the overall transmitted power, which ultimately depends upon the transmission line impedance as well as the angle between the end line voltages. The main idea of series compensation is to decrease the overall transmission line impedance, as can be seen from this diagram. As you can see from here, the power is equal to V1 V2 by X into sine of delta 1 minus delta 2. While the shunt compensation works on the voltage profile, the series compensation works on decreasing the overall transmission impedance as well as the phase angle control. Now let us see how it does. Actually, we insert a capacitor in series with the transmission line, which decreases the overall effective impedance. Let us see how. A compensating capacitor is connected in series, which cancels a portion of the actual line reactance, and thereby the effective transmission impedance is reduced as if the line was physically shortened. Now let us see what is the effect on the active power and reactive power by this compensation. As you can see from here, the real power transmitted is given by P is equal to V square by 1 minus K into X sine of delta, and the reactive power supplied by the series capacitor is also dependent upon the impact of the compensation. The transmittable power rapidly increases with the degree of series compensation K, and the reactive power supplied by the series capacitor also increases sharply with K and varies with angle delta in a similar manner to the line reactive power. So series capacitors have been used extensively in the last 50 years throughout the world for the compensation of the long transmission lines. Thyristor controlled series compensator, that is TCSC, is a capacitive reactive compensation which consists of a series capacitor bank shunted by a thyristor controlled reactor in order to provide a smoothly variable series reactance. As you can see from here, the TCSC can control the line impedance through the introduction of a thyristor control capacitor in series with the transmission line. So we can say that it is actually a variable inductor in parallel with a capacitor. Now how is the overall impedance affected can be seen from this diagram. As you can see from here, the equivalent impedance is given by J equivalent is equal to minus J 1 upon omega C minus 1 upon omega L. Now the overall working principle of the TCSC basically depends upon this formula. How it is? It basically depends upon the value of this omega C minus 1 upon omega L. If omega C minus 1 upon omega L is greater than 0, the reactance of the fixed capacitor is less than that of the parallel connected variable reactor, and this combination provides a variable capacitive reactance. If both the values are equal, that is omega C minus 1 upon omega L is equal to 0, a resonance develops that results in infinite capacitive impedance, and this is an unacceptable condition. So we normally do not operate TCSC under these conditions. And the third condition is if omega C minus 1 upon omega L is less than 0, then the combination provides a variable inductive reactance. So we can say that it basically works in two modes. One is the capacitive mode, the other is the reactive mode. And normally we operate the TCSC in the capacitive mode. Now this is the WSCC 3 machine 9 bus system which we have discussed earlier, and in this we have implemented a TCSC in the middle of this transmission line. Now let me show you the TCSC in Simulink environment. As you can see from here, this is the 3 machine 9 bus system which we have discussed earlier. In this we have used this TCSC in the middle of the transmission line. Now as you can see from here, this is the TCSC. This is its control scheme and its firing unit. Let us see how it works. As you can see from here, the TCSC basically comprises of a thyristor controlled reactor. So this is the thyristor controlled reactor which is in parallel with the capacitor, and all these three are in the three phases. Now the basic thing is we have to control or we have to generate the firing pulse for all the thyristor. That is done with the combination of the control scheme and the control unit and the firing unit. Let us go back. Now one important point which you must keep in mind is that whenever the TCSC is operating in constant impedance mode, it basically utilizes the feedback voltage and current in order to calculate the impedance. We basically give it a reference impedance, and that is compared with the impedance it calculates with the help of that feedback voltage and the current. How it does is, this is the control unit. The voltage from the TCSC is fed to it along with the line current, and this is the Z reference. Now as I told you that there are two modes in which the TCSC works. One is the capacitive mode and the other is the inductive mode or the reactive mode. Now in this case, for capacitive mode, the impedance has to be kept in the level of or in the range of 120 to 136, while in the inductive mode, the impedance is to be kept in the range of 19 to 60. In our model, we have operated the TCSC in the capacitive mode and we gave the reference of Z, that is Z reference value, as 122. Now coming to the control system, this is the impedance calculation block which basically works with the help of this input TCSC voltage and the current. It calculates this impedance which is then basically given to a PI controller. So we have a separate PI controller for the capacitive mode and a separate PI controller for the inductive mode. So this is the controller for the capacitive mode and this is the controller for the inductive mode. So what it has done is basically it has compared the Z reference with the Z measure which was given by the impedance calculation block, and ultimately it generates this alpha. Now this alpha is then, let us go back again. Now this alpha is then fed to this firing unit. So basically the firing unit has three inputs. One is the alpha which is calculated by the previous block, that is the control unit. The other is the line current and the third is the IRMS. What it basically consists of? Let us see. The firing circuit basically uses three single phase PLL units for synchronization with the line current, as you can see from here. It basically consists of three single phase PLL units for synchronization with the line current. Now one important point to be noted is that the line current in this case is used for the synchronization for PLL. Now this is the main difference between the series and the shunt. If you recall the control scheme of the STATCOM, in that case the line voltage was used for the synchronization, whereas in case of TCSC we mainly use the line current for the synchronization because the TCSC voltage can vary widely during the operation. So this is the main point which is to kept in mind. So through this the TCR pulses are generated which are then fed back to the TCSC. So this is the whole TCSC control scheme in the Simulink. Now this is the 3-machine 9-bus system which is implemented with TCSC. As you can see from here, the TCSC has been inserted in the middle of the transmission line and a 3-phase fault was basically inserted at different locations, and we compared the performance of the various locations in terms of the load angle. So I have already discussed this in our earlier sessions also, that basically the performance of the load angle variation is used to see the effect of the TCSC. Now this model was made compatible with the real-time simulator, in which I created this top model of the OPAl RT based system which was implemented with TCSC. As you can see from here, there are two subsystems. One is the master subsystem which contains the main circuit, and the other is the console subsystem which basically consists of the scope, and the third thing is this power GUI which is used for the initialization of the power system model. This is the console block in which I have inserted this OPCOM. I have already discussed this in the previous sessions. Now before coming to the results, let me show you how to run this in the real time. Now here I will create a new project. Either I can go here or else I can go to the file, create a new project, new RT lab project. I give it a name, let's say TCSC 1, it's already created, so I'll create a 2, TCSC 2 and finish. So as you can see from this project explorer, a new project has been created. The next task is to add the model. So just go to models, add existing model. Now it is highly recommended to import a copy of an existing model instead of creating a direct link to it. So I will just import it and browse. So this is where my model is. So as you can see from here, the model has been added to my main project. The next task is edit the model. This will open a new MATLAB window. In the meanwhile, I'll just set the development properties. Red Hat. Again go back. Let me check if the model has been opened. It's still taking some time. In the meanwhile, let me close the earlier version. It will unnecessarily create some confusion, so I'll just close the earlier version. Yeah. Now build the model. It's taking some time. You can see the progress here. The model has been built. The next is assign target to subsystems. Clean target. Again go back. Set the execution properties, because in this case we are not using any external hardware. So the real-time simulation mode will be software synchronized. Load the model. So you will see once the model has been loaded, you will get this kind of window and automatically generated by RTLab during compilation. This means that your model has been loaded. The final step is the execution of the model. So execute the model. We just run it. So these are the results which are coming in the real time. I'll just show you them. This is basically current, voltage, power, all these values. So these are the results in the real time. Apart from that, we can also see the load angle, variations. Take some time. Actually, we inserted a fault at 15 seconds and it was given for 1 second. So now let us see what are the results for the variation of the load angle. So these are the results which I got. This is the variation of the relative load angular position, that is load angle 1 to 2. So basically, as I told you, that we inserted the fault at different locations and then we compared the result. So this is the result for the location number 2, and this is the variation of relative load angular position 2 and 3. Similarly, variation of relative load angular position, load angle 3 and 1. Now for different fault locations, this is the comparison for the time taken to attain stability at load location 1, location 2, location 3 and location 4. This is the result for uncompensated and this is the result for the compensated. This is for 1, 2, 2, 3 and 3, 1. Similarly, we have a comparison for different fault locations for the steady state stable values and also the maximum overshoot for the various locations. Now these are the observations. The 3-phase short circuit fault at generator and location 2 and location 4. Now let us see what is this location 2 and location 4. This is basically the generator end. I'll show you. Yeah, this is location 2 and location 4. So from the results we saw that the fault at these two locations, that is near the generator, was the most severe one, while one at location 1 was lesser and the one location 3 that is near the load was the least severe. So that is very important, that what is the effect of the fault location also we have studied with and without TCSC. Now going back, the fault at the middle of the transmission line, that is location 1, is more severe than the same fault occurring at load site location 3. And we have seen that the system with TCSC shows a much faster operation in damping post-fault oscillations rather than in the system without controller. Now these are the results which are quite similar to the one we obtained for the StatCom. However, there is one main important difference, which is here. The steady state error in the stable value is nearer to 0 when implemented in the uncompensated system rather than with the TCSC, in which the error is much large. This is the main difference between the results of TCSC and the StatCom. And for location 2, because as I told you, the graphs which I showed you were for the location 2, that is near the generator number 2. With the incorporation of TCSC, the maximum overshoot is reduced to approximately 1/5, 2/5 and 4/5 of the value of uncompensated load angle 1, 2, 2, 3 and 3, 1 respectively. Now these were the results of the comparison of the various load angles at different fault locations. We also studied what is the effect of the change in the fault clearing time. As I told you that in this case we had inserted the fault at time 15 seconds and the fault clearing time was taken as 1 second. Now let us see what is the impact of the change in the fault clearing time. So accordingly, different fault clearing times were selected. As you can see from here, 0.2, 0.4, 0.6 and 0.8 and 1, and accordingly the time taken to attain stability was attained in this way. Similarly, the steady state stable values were also found for the various fault clearing times, as well as the maximum overshoot of the various load angles at different fault clearing time was calculated. These are the observation. We can say that the time taken to attain stability for an uncompensated system increases with the increase in the fault clearing time. However, for a compensation system using TCSC, it remained nearly the same. Similarly, the steady state error decreases with the increase in the fault clearing time for the uncompensated system, whereas using TCSC, it remained nearly constant. Also, the maximum overshoot increases with the increase in the TCSC for an uncompensated system, whereas it remains nearly the same for a TCSC based system. So these were the various observations we found by changing the fault clearing time. So in today's session, we have seen the basic working principle, control scheme and real-time simulation of TCSC using OPAl RT. We also saw what is the effect of the change in the fault location as well as changing the fault clearing time on the various load angles for the TCSC. Thank you.